All right, so what we're going through today is we're going to work on the worksheet that I gave you guys, which is going to have the names of the ionic and covalent compounds on it. I'll show that to the video. It's right here. All right, so take a look at this. You're naming ionic and covalent compounds. All right, after you name them, I want you to find the molecular mass of them. Don't just look it up on your phone. All right, and then show the Lewis dot structure. Now I'll go into, there are differences in Lewis dot structures between ionic and covalent compounds, and that's important. But for this first part, let's talk about naming ionic or covalent compounds. So let's say I have something like, oh boy, let me find one in here that would be a good example. Let's say I have NH4 and I have Cl. Now, this may or may not have parentheses around it, but what I like to do is throw parentheses around it because this tells me that it's a polyatomic ion. Usually, you have to be pretty familiar with your polyatomic ion sheet, or you're just going to flip right through it and look through there and be like, are these compounds in there? Now, the first thing I did when I looked at this in order to get to there is I was like, is this two compounds? No. Well, does it have a polyatomic ion? Yes, it does. NH4 is going to be a positive polyatomic ion. It's one of the very few that there are, and that's ammonia. This is like what you use to clean your clothes. It's like what makes urine smell the way that it does. And when it bonds with chlorine, it actually gives pools the very unique smell. So, think of that. All right, so here is ammonia, and it's bonded with chlorine. Okay, now how would I say this? Well, I would say the polyatomic ion name. So I would say ammonia. Right, and then I say this, which would be chlorine, but instead of ene, I'm going to put IDE at the end of it. So it's going to be chloride, C-L-O-R. Now, instead of I-N-E, it's going to be I-D-E, chloride, right? Not C-H. Don't take spelling from me, I'm a chemist. All right, so ammonium chloride. Very cool, so we have that. Now, for this one, I want you guys to find the mass, right? And I'll do that in blue. Right, and I'm not going to make you draw the Lewis dot structures for polyatomic ions. We just ain't there yet, Chief. But I will ask you to find the mass form. So mass for this is going to look like this. What's the weight of nitrogen? It's 14.01. So I usually put my elemental symbol right there, and I say 14.01. Okay, you only have to go with the 4 sig figs for these. Please don't go any further than 4 sig figs because you're just going to make my head hurt, and I can't do math like that big. Usually I just do quick maths. All right, so how much is hydrogen? Well, I have 4 hydrogens, so I'm going to write an equation here where I have 4 times the weight of hydrogen. What's the weight of hydrogen on the periodic table? It's 1.01 AMU. All of this is going to be in AMU. I'm neglecting to put it in here to save us some time. So I have 4 times that. All right, and now I'm going to also combine chlorine. What's the weight of chlorine? Is it 35.45? I don't know, I'm generally asking. 35.45? Yeah. All right, so chlorine is 35.45 AMU. Now all of this is in AMU. So I just want to add all these up. I only have 1 of them, that's why I only have 1 here. I have 4 of these, so I'm multiplying it by 4 so that it represents my chemical formula. All right, very cool. So 14 plus 4.04 is going to be what? It's going to be 18.05. So I have 18.05 added to this, and that ends up being 4. No, that's 5. 53.5. Awesome. So 53.50. So I have 53.50, and AMU can be converted directly to grams per mole. So just write it like that. You don't even have to put AMU over here, just convert it directly to grams per mole. How do we know that? We added it all up on the periodic table. And I'm not sure if you guys can see everything I'm working on, but there it is. There's my math for it. All right. Now, if you have a polyatomic ion, I want you to stop right there. You're good. You're done. You completed it. Very good. Move on. Now, if it's not a polyatomic ion, I'll show you how to do it. Okay? So you guys can use, everybody have this written down. Take a little bit of time. All right. So that's how you do the polyatomic ion ones. And it's mint water. It smells amazing. Anyway, so clear all this off, make sure it's nice and dry. Moving over to this side, over here. Okay. So let's say we have something else. I'm going to go with a very standard, stereotypical salt. All right, I'm going to say Na, and then we're going to have Cl. All right. Cl is a minus, and Na is a 1 plus. If you look at the periodic table, the way I laid it out for you guys, 1 plus, 1 minus, you should immediately think that's a salt. And why is that? Well, 1 is going to be a metal, which is sodium, which is kind of shiny. All right, plays like, you know, kind of like Play-Doh. Not that you would ever touch it because it bursts into fire and air, but if you could, it's kind of like Play-Doh texture. Anyway, chlorine is going to be on the far right, and that is to the right of that staircase. So it is an organic molecule, or you can think of it as being a non-metal. So metal, non-metal, charges balance, I'm thinking it's going to be ionic. Okay, so it's an ionic compound. How do I name it? Well, I put the cation ion first, right, and I just say the name. This is sodium. So I have sodium, and then I have chlorine. Well, again, when we have chlorine, we put IDE for ionic compounds, so we have chloride. All right, so we have chloride. So that's sodium chloride. Very cool. Now the next part of this, I want you to find the mass. So I'll do that all in blue. What is the mass of sodium? 32.45? No, it's not.
39.09.
So 39.09, and again, I can put AMU if I really want to. And I'm going to add that to chlorine, which is 35.45, right? Perhaps?
35.45, yes.
Awesome. So 35.45. Okay, so I just add these two together. It's fairly straightforward. So 9 and 5 is going to be 14. Right, so I carry the 1. We have a 5 there. Okay, and then we can move over to here. So 35, and that again is going to be 14. I carry the 1, and I have 4 and 3, which is 7. Very cool. I can write grams per mole, all right, because it's a 1-to-1 conversion between A and mu. So we have 74.54 grams per mole. What does that mean? Well, if I have 74.54 grams of this substance, of this salt, I know that I have 6.022 times 10 to the 23rd molecules of sodium chloride, which is 1 standardized unit. Okay, very cool. All right, now moving on to how I want you to draw a Lewis dot structure. I'm going to do this in red. Now the difference between ionic compounds and covalent compounds when you draw the Lewis dot structure is one is going to be shown stealing the electron, the other one is going to have a bond. Okay, so first I'm going to draw sodium. And the rules for drawing sodium are what? We look at the outside charge on it. How many valence electrons does it have? It has 1. So we just put it right there. Now I'm putting it to the right, and then you fill it like that. So you fill it around towards your left hand, right? Or you can think of opposite of clockwise, right? But sodium only has 1, so we just put it there. Now chlorine, I'm going to place a little closer because chlorine just needs 1 to be perfect, all right? And because chlorine just needs 1 to be perfect, as I fill it, I'm going to put it around this electron because it's going to steal it. Okay, so we have 1, 2, and there's 7 electrons of chlorine, right? Because it's 1 minus, right? So it's 1 away from perfection. Here is 3, here is 4, and we have 5, 6, 7. Do you see how it's kind of stealing that electron right there? Now in the Lewis dot structure, you just leave the dots there. In a covalent bond, you would draw a line indicating that it's shared between them. But in the Lewis dot structure, this is the way that you represent it. So let me do a covalent bond real quick. So let me flip over to a page you guys haven't done yet. I stapled this one backwards. All right, so let's take a look at this. All right, let's do CO, good old carbon monoxide. Okay, so I have C and O. Now recognize that I draw the O as being a capital letter. Don't get in bad habits of putting them as smaller letters because sometimes you might mistake things that are actually 2 elements as 1 element. Okay, so just make sure you do that, or sometimes you can put like little weird dashes in it, which is why I like to do blessing. All right, so here, what do we do? Well, we first name our compound. What is it? We don't have to put monocarbon, right? We just put carbon because it's just one of them. So we just say carbon. And then here we have to put the moniker in front of it of mono, di, tri, tetra, penta, hepta, hexa, octa, nona, deca. I want you guys to remember that. Please memorize that forever. All right, so here we go. We have oxygen. How many do we have? We have one, so we would say mono oxide. All right, instead of oxygen, again, we drop it. We put IDE, O-X-I-D-E, monoxide. All right, very cool. So now we have it. We've named it. What do we have to do next? We have to find the mass. How do we find the mass? Well, the weight of carbon is going to be, right, 12.01. And we are going to add that to the weight of oxygen, which is 15.99. Again, you'll see that I'm doing for significant figures. I put my letters right above it. Okay, you can see I'm putting my letters right above it right there. So carbon, oxygen, here we go. 12.01 plus 15.99 is going to be what? 28. All right, so 27.99, right? Maybe, nope, actually exactly 28, right? Very good. All right, I was wrong on that. So 0, 0. So 28, and what's our units? Grams per mole. So that means if I have 28 grams of carbon monoxide in the form of dry ice, let's say, I have exactly 1 mole. All right, we'll use this later on this year. We'll blow stuff up with it. We'll take dry ice, we'll throw it in a 1-liter bottle, and we'll try to predict when it's going to explode based on the pressure and how its rate of turning to a gas. Should be fun. All right, now we get to the hard part, the Lewis dot structure. Well, what's the Lewis dot structure of carbon? I always do carbon in black usually, but we'll do it in red just to show that it aligns with number 3 on the board. So carbon has 4. So I would draw 1, 2, 3, 4. Now these bonds in carbon, it can form up to 3 bonds, okay, in one direction. And that's going to be important here in a minute. So we have carbon monoxide, all right, so I'm going to draw oxygen next to it. All right, and I'm going to draw it in blue just to kind of show what its electrons are going to do. Now, typically, it's going to have 2 lone pairs because it has 6 electrons. So we have 1, here's 2, here's 3, here's 4, 5, and 6. Now, we'll see here that there's 2 that are unpaired. What's going to happen here? It causes instability. That instability means that carbon wants to form 2 bonds. Okay? And so instead of drawing them as 2 dots by one another, we are just going to draw a double line, indicating that there's 2 bonds. And then there are 2 electrons that are unpaired with carbon. All right, so how much does carbon have total? Well, it has 1, 2, 3, 4, 5, 6. So carbon has 6, and oxygen has 2, 4, 6, 8. So here we have carbon monoxide. All right, and we can also really draw those as a lone pair if we really wanted to. I'm gonna leave it just like this. This is how you would draw carbon monoxide. So it's not a very stable molecule because there are 2 bonds that are unaccounted for, right, and are not sharing to get 8. You cannot have more than 3 bonds, and so that is just how this works out. Anybody got any questions on this? Very cool. All right, so that is how you do an ionic and how you do a covalent molecule. That is how you find the mass and how you show the Lewis dot structure. And I want you to do these for all the ones that are going to be diatomic, meaning that they have 2 atoms in there. I don't want to see them for every single one. That would be very difficult, and I'm sure you're going to encounter some that are exceptions. Yes, there are some that are exceptions, especially with sulfur and phosphorus and some other elements. Again, that has to relate with different kinds of harmonics that are kind of exceptions. And the reason why they exist is you can think of them as being lower energy solutions for stability, or as being ways that those molecules harmonize to form a stable wave. Any questions? All right, what's the question?
Which one is more dangerous, carbon monoxide or dioxide?
All right, so carbon monoxide is going to be more reactive, so I'd say it's more dangerous. So CO2 takes generally longer. I think your blood has an affinity of 6 times for this one than it does for anything else. So like monoxide kills you rather quickly. Not related to how it bonds, but all right, let me stop.